What we were doing in our last class?
Ma'am, laws of motion.
Oh, we were just about to start that, right?
I think we did the introduction. You told about the different types of forces.
Contact force and field type
Yes,
of forces, correct?
Yes, ma'am.
Yeah. So just go ahead from there. We'll discuss about the laws that are mentioned in that chapter, like first law, second law, and third law. What is Newton's first law? Can you tell me?
The law of inertia.
Yeah.
Like
Law of
inertia.
Yes. Can you state it?
An object will continue to remain in motion until it's disturbed by an external force.
Correct. So that means what is inertia actually?
Inertia, the tendency to remain unchanged.
Yeah. Tendency to remain unchanged. Correct. So I'll just share the screen of that NCERT. Yeah, I think we just have talked about Aristotle's fallacy,
Yes,
right? It is initially assumed like just to change the state itself, we need the external agency. That is what was the assumption.
Yes.
But later we came to know that to move in uniform motion, we don't need any external force. Okay.
Yes.
So that is what the false, notion about the concept of inertia was there. Later, yeah. So the first law of motion can now be stated as every body continues to be in the state of rest or in the state of uniform motion unless compelled by an external force. Okay. So if it is rest, it will be in rest. If it is in motion, it will be in motion. Okay. And inertia can be classified as two types, like inertia with direction and inertia in motion. Inertia of direction means it is the inertia which tries to oppose any change in the direction of motion. Okay. And inertia of motion means it tries to oppose the the change in its speed. Okay. Or if it is in the state of rest, it tries to oppose the state of rest to the state of motion. Okay.
Oh.
Yeah. So
inertia of motion and direction, right?
Yeah.
Okay. Yes.
Yeah, so they are just finally trying to summarize what is inertia. So it is the resistance to the change. Okay, so body is at rest, it will be at rest. If it is in motion, uniform motion, okay, so unless compelled by an external force, it will be in that state itself. Okay, so that is like if the net external force on a body is zero, its acceleration is zero. Yeah. So acceleration can be non-zero only if there is some net external force. Okay. So here they are again, trying to somewhat give an idea of acceleration. So this is the, the other way of, saying your first law of motion. If there is no force means acceleration is zero. If there is some acceleration, okay, then there must be some force. Okay. Is there any other point that needs to be highlighted? Yeah. So the next comes is the concept of second law and momentum. So do you know what is a momentum is? Do you know what is a momentum?
Hello?
Are you talking? Yeah. Yeah. Tell me now.
Momentum is, I know the formula, it's m into v, right? Mass and velocity.
Correct. So mathematically, you can say the momentum which is represented by P. Okay, P is the notation for momentum. Yeah, I mean, it's a standard notation. Okay, just a minute. Yeah. So it's a physical quantity which tells you the quantity of motion or the amount of motion. Okay, momentum will actually tell you the amount of motion which is given by the product of mass and velocity. So then by default, your momentum is also going to be a vector quantity.
Yes.
Correct? And the direction of momentum will be along the direction of velocity itself. Okay. So, and what will be the unit of momentum? So mass is kg, velocity is meter per second. So you get kg meter per second minus 1. Can you tell me the dimensions of momentum?
MLT minus 1.
MLT minus 1. So the dimension of the momentum is MLT minus 1. Okay. Now, like, why we need this? What is the significance of it? Let us say there's a car. Okay, there's one car. It has some mass. Okay, some mass. Okay, let me just take it as some capital M. And it is moving with some velocity v. Okay. So now let me say there is, another, okay, let us say some cycle or bike is there. Okay, just imagine like cycle or bike is there and it has a mass like small m. This is also moving with the same speed v. Okay. Out of capital M and small m, which is going to be more? Which is going to be more?
Capital M.
Yeah, obviously, car mass is greater than the cycle or,
Yes.
the bicycle or the bike mass. So I'm just taking a general example. But both are moving with the same speed, right?
Yes, ma'am.
Now, in order to bring them to rest, okay, if I want to bring car to rest or if I want to bring the bike to rest, which require more force?
The car.
Definitely. Okay, so that means in order to bring a change in their state of motion, okay, that is decided by mass as well as velocity. It is not just decided by mass alone. It is not just decided by velocity alone. Okay, for example, there is a, some, you can imagine like just one wheel is there or some circular disc is there. Okay. So now let us say this is of some, both are of same masses, but this is moving with speed like 2v. This is moving with speed like 0.5v. So now if I want to bring it to rest, okay. So if I want to bring it to rest, which requires more force?
The 2v1.
Yeah. Like even though the masses are same, the required force to bring it to stop is greater for the object which is moving with more velocity. Okay. So in that way, if you take, yeah, so this is the importance of your mass and velocity. Okay. The importance of mass and velocity is that togetherly it decides how much is the quantity that is in motion or what is the quantity that is in the amount that is in motion. Okay. So that's why we call it as amount of motion or the quantity of motion. Mathematically it is fine, m into v. Okay. But why we need it, like in order to discuss like which requires more energy to bring it to stop, that will tell you which is having more motion in it. Okay.
Yes, ma'am.
Yeah.
Yes, ma'am.
Is that clear?
Yes.
Yeah. Yeah. In the, like, do you have NCERT with you right
Yes,
now?
ma'am, I have.
Yeah, just go to that page, like page number 93.
Yes, ma'am.
Yeah. So like they're telling like under the heading of momentum is a vector quantity. Hope you can see that.
Yes, ma'am.
And I mean, I can share it. The problem is like if I keep on, switching from one screen to other screen, now it is appearing blur nowadays.
No, it's
I don't know
not a
why.
textbook, so
Huh.
I hope.
Huh. So suppose if you have a lightweight vehicle, there are some points are given.
Yes, ma'am.
Just the example as I told, there is a lightweight vehicle and there's one heavy vehicle. Okay. So both are parked on a horizontal road. We all know that much greater force is needed to push the truck than the car. Correct?
Yes, ma'am.
Like if you are imagining like you are pushing from outside, you are not starting the engine. So the point, obviously, compared to car, the truck requires more energy. In the same way, in the second example, they are talking about there are two stones. One is light and the other is heavy. Okay, which are dropped from the top of a building. Okay, so you have two stones. One is light stone, one is very heavy stone, and a person on the ground will find it easy to catch the light stone when compared to the heavy stone. These are all like common experiences, right? So the mass of a body is thus an important parameter and determine the effect of force on its motion. Correct?
Yes, ma'am.
So both mass and velocity both will decide, and that is why we are defining a quantity called as momentum. Okay, and there is one example of the bullet is given. The speed is another important parameter to which has to be considered. Like a bullet fired by a gun can easily pierce a human tissue before it stops, resulting in casualty. Correct?
Yes, ma'am.
The same bullet fired with a moderate speed will not cause much damage. Thus, for a given mass, the greater the speed, greater is the opposing force needed to stop the body. Correct?
Yes, ma'am.
So taken all together, we say like the product of mass and velocity as momentum. Okay?
Yes, ma'am.
Yeah. And there's one important fact given there. The greater the change in the momentum in a given time, the greater is the force that is needed to be applied. Correct? If the like within a 1 second itself, if the momentum is changing drastically, then it means like the more the change in momentum in a given time, obviously you require more force to stop it. Okay.
Yes, ma'am.
Example of taking catch in the cricket sport is given. So a seasoned cricketer catches a cricket ball coming in with great speed far more easily than a novice who can hurt his hands in the act. Correct? Like if we try to go and catch it, we may not be so proficient enough to catch it. Like we may definitely get it hurted, but the cricketer, like he's been trained for that. He know the way of taking the catch. It may be like what actually the cricketer will do is the cricketer allows a longer time for his hands to stop the ball. So initially, I mean, usually what he does is he just catch the ball and he will not stop his hands there itself. He just brings it back.
Yes.
Yeah, you may have noticed he draws the hands in the backward in the act of catching the ball.
Yes.
He takes his hands back also after catching. But what we try to do is usually we just hold it and we just stop there itself. So all the momentum, whatever is carried by the the ball is been instantly applied on our hands and we get hurted. Okay, but with the like in the training process, what they do is like you will hold it, and before bringing the object to rest, you give sufficient enough time. Like you also bring your hands little in the backward direction. Okay, so that you are giving some extra time to it. Okay.
Yes, ma'am.
Yeah, so that is one example. Like sometimes they will give some situation like this and they will tell you to explain the concepts behind it. Usually with inertia or momentum, you can expect one question. They'll give you some scenarios like this. Okay. Yeah, the conclusion is clear that force not only depends on change in momentum, but it also depends on how fast it is changing. Correct?
Yes.
More the time if we give, lesser will be the impact. Yes or no?
Yes, ma'am.
Yeah. So that is how we try to define like the same force for the same time causes the same change in momentum for different bodies. This is just we are trying to say, like, your Newton's law in a different way. Like the same force for the same given interval of time causes the same change in momentum for different bodies. The bodies are different, but we are applying the same force and we are applying it for the same time, then the change in momentum what you see is going to be same. Okay.
Yes.
So by that what we say is, this is the important statement, the rate of change of momentum of a body is directly proportional to the applied force. And where does it takes? It takes place in the direction in which the force acts. Okay, the rate of change of momentum. How can we write rate of change of momentum?
Delta.
So the rate of, so like the rate of change of momentum is directly proportional, like, to force. So I'll write F is directly proportional to delta P by delta T. And if our delta T is sufficiently small enough, I can replace this by dP by dt. The time interval, we are taking small time interval. And under SI system, the constant of proportionality, like if you have a proportionality, what we will do, we have to introduce some constant k into dP by dt. But in SI unit, it is found that constant of proportionality is 1. Okay, for SI system. This is a system dependent constant. Okay. So what you get, your F is equals to dP by dt. But what is P? So I can write d by dt of m into v. Correct? d by dt of m into v. But usually mass is constant, so it will not change with time. So I'll take it out of the differentiation. Then what you get? dv by dt. Correct?
Yes.
So, but what is this dv by dt? Rate of change of velocity will give you what?
Acceleration.
Yeah. So this is how we usually say force is equals to product of mass into acceleration. Okay. So this is usually we say like second law of Newton's second law. Okay. So F is equals
to derivation.
Huh?
Can this be asked as a derivation for force?
Quite less time this has been asked.
Okay.
This particular derivation is quite less time they have asked. Okay. I mean, just you can start from here, just at 3 step. Force is proportional to dP by dt, which is statement. Then put for P, then just write P as m into v, and we know that dv by dt is acceleration. Okay. This is the usual form of Newton's second law. But if we have the mass is not constant with time, if mass is not constant with time, so then what happens? Like force is equals to dP by dt, that is like d by dt of m into v. So it's like now both are variable in time, correct? Mass is also a variable in time. Velocity is also a variable in time. So what we will do? So now first I differentiate mass like dm by dt. The rate of change of mass, I'll keep velocity as it is, plus I'll keep now mass as it is, like m I'll keep as it is. Now I differentiate velocity. Yeah. So this is the actual form of derivative of the force, like dm by dt into v plus m into dv by dt. Now if mass is constant, we know that the differentiation of a constant is 0. I think you know that, correct? The differentiation of a constant is 0. Okay. So like in that case, this term goes to 0 if the mass is constant. Again, we'll get back the earlier equation. F is equals to m into a. Okay.
Yes.
So here this can also be written as dm by dt, dm by dt into v plus m into a. So this particular equation can be considered during the rocket launching cases, because there as the fuel is burning in the rocket, okay, so the mass keeps on reducing, right? And we cannot ignore that change in mass. Okay, with the time, so much amount of fuel will be burning, and because of that burning, you are getting some exhaust out of the rocket, and that exhaust which is coming in the backward direction will give you a momentum in the forward direction. That's how the rocket propulsion works. Okay, so I mean, definitely, I think you right now agree for the fact that the mass is changing in the case of rocket.
Yes,
correct? Yeah. So there you cannot just consider F is equals to m into a. If you are doing anything with the case of rocket problems and all, definitely the rate of change of mass to be considered. Okay, is that clear?
Yes, ma'am.
Any doubt here?
No, ma'am. Just a minute, I'll just copy it.
Yeah.
Okay, done, ma'am. Thank you.
Just 1 minute. Yeah. Can you hear me?
Yes, ma'am.
Yeah. So going ahead. Now we'll just try to define. We already defined what is a force, which tells you like it's an external agency which is applied to change the state of uniform motion or the state of rest.
Yes.
And we also found out that it depends on not just on the product of mass and velocity, but also on the change in momentum, like change in the rate of change of momentum. That's how we defined our force. Now, if I want to define the unit for force, like we know that force is nothing but m into a. So it implies what will be the unit of force? Yeah, it's like kg meter second minus 2, which we have labeled as Newton. Okay, we call this as Newton or newtons and represented by capital N. Okay.
Yes,
ma'am. And can you tell me the dimension of force?
I don't remember.
No need to remember. You can work here, no?
Okay.
So it is m.
M then LT
minus 2. That's all.
Yes, ma'am.
MLT minus 2. You can look into unit and you can tell like kg meter second minus 2 means kg means mass, m means length, second minus 2 means t minus 2. Or you can remember like mass, acceleration is L by t minus 2, no?
Yes.
LT minus 2. You can just put it. Okay?
Okay.
That is how you write the dimension for any physical quantities. Okay?
Yes, ma'am.
Yeah. So now, coming back. There are some facts that are discussed in terms with force. So now if I want to define 1 Newton, how can I define? So what we usually, if you want to define any unit, what we'll do, we'll take one equation corresponding to that unit and we make all the parameters there as unit, like we'll make it 1 and then that will be equal to the corresponding unit. Like what we'll do is, let us say there is 1 kg mass. Okay, we have 1 kg mass and some force acts on it and it produces an acceleration of 1 meter per second square. Okay, then the force is said to be equal to 1 Newton. Okay, a force is said to be 1 Newton if it acts on 1 kg mass and produces an acceleration of 1 meter per second square, then that is equals to 1 Newton. Okay.
Okay.
Yeah. So now, like some points with respect to your second law. If I say the applied force is 0, then what you will get? Your acceleration is 0. Do you agree? If
Yes.
F is equals to 0, like F is equals to m into a. If force is 0, then the product of m into a must be 0. But the point is m cannot be 0, no? Mass is like, it definitely exists unless we are talking about some particles which are having mass. So if mass cannot be 0, then acceleration must be 0. Correct?
Okay.
That means you are going to the case of first law, like where when there is no force acting on it, the acceleration is 0. The object will be at rest, or it will be just moves with uniform velocity. Okay?
Yes.
Yeah. In the second law, you can even write it with the component notation. I think you know that the force is a vector quantity, correct?
Yes.
Force is a vector quantity. So can you see my writing screen?
It's loading.
Yeah.
Yes, ma'am, I can see.
Yeah. So we can say that force, if I want to represent it in 3 dimensions, how can I write? F is equals to Fx into I cap plus Fy into J cap plus Fz into K cap, correct?
Yes, ma'am.
Yeah. So now, if I want to write the F is equals to ma, we already know I can write it in component notation. So I can say Fx will be equal to mass into acceleration along x-axis. Similarly, Fy is equals to mass into acceleration along y-axis. And Fz is equals to mass into acceleration along z-axis. Okay? The force which acts along some axis can change only the acceleration along that axis. Okay? If I apply a force in x direction, it cannot affect my acceleration in y and z direction. Okay? It can change only the acceleration in x direction only. Okay?
Yes, ma'am.
Yeah. Moving ahead. Yeah.
Yes, ma'am.
Just a minute. Can you see the screen? Still loading. Can you able to see the screen?
It's just a black
Huh?
screen.
Sorry?
Still a black screen.
Oh, okay. Let's see. Very well.
Yes, ma'am. The NCERT, right?
Huh. Can see, no? No?
Yes, ma'am.
Yeah. So the second law of motion given by is applicable to a single point particle. Okay, what we just said, no, F is equals to m into a, that you can apply for a single point particle. Here, the force F in the law stands for the net external force. Like there is one single particle, and if there are two forces are acting, like F1, F2. Now, let us say its mass is m, then the net force will be equal to m into a. Okay? So if I say this has been moving with some acceleration a, then m into a is not equal to F1 or is not equal to F2. It is equals to the F net. And also net force, how do you find out? You have to do vector sum. Correct? Your vector F1 plus a vector F2 will be equal to vector F net. Okay? So how do you find out the resultant of two vectors? How do you find out?
That formula A square plus B square
Yes.
plus
Yes.
2AB cos theta.
Yes, under root. The resultant of two vector is square root of a square plus b square plus 2ab cos theta. That means here you should see what is the angle between F1 and F2. Okay, you have to see what is the angle between, like F1 is acting in this direction, F2 is acting in this direction. The angle between their direction is theta. So F1, you should see their magnitudes, and then you have to calculate the net force, and that will be equal to M into A. Okay. Yeah. So next is, when we say F is equals to M into A, it applicable only for the external forces, and A stands for the acceleration of the particle. It turns out, however, that the law in the same form applies to a rigid body, or even more generally to a system of particle. Like rigid body means the elongated objects, like normal, whatever, like in our daily life, we are not just having some point particles to deal with, right? We have a car which is moving, we have a vehicles that are moving, we have some other objects which is being kept at some rest, correct? The bulk objects will be there. That is what we call it as a rigid body, okay, which can be imagined like a system of particles. There's a one chapter, like chapter 6 or 7, where you entirely learn about the rigid bodies and system of particles. But earlier, first 2, 3, like up to chapter 4 or 5, we'll just restrict ourselves to the discussion of particle in a motion, like a single particle which is moving. Okay, we don't consider an entire rigid objects. Okay. And see, and F refers to the total external force on the system, and A refers to the acceleration of the system as a whole. More precisely, A is the acceleration of the center of mass of the system, about which we shall study in detail in chapter 7. So you right now you ignore this, not necessary. We'll understand later what is a center of mass and all. So now any internal forces in the system are not to be included in F. Internal forces like, you know, the gravity, force of gravity between two masses. Okay. So when we are applying your F is equals to MA for a rigid body, we just need to consider the external applied forces. Okay. Yeah. And the next point is, and I mean, these are all some typical points. The second law of motion is a local relation, which means that the force F at any point in space at a certain instant of time is related to A at that instant. Acceleration here and now is determined by the force here and now, and not by any history of the motion of the particle. For example, I have a particle here. Now I apply a force like F1. Okay. What I'm doing, I'm applying a force like F1, and let us say I got an acceleration like A1, which can be written like F1 by M. Do you agree?
Yes.
Yeah. So now, and after some time, I make this force goes to 0. Okay. After some time, I had done, force goes to 0. And now I apply a force F2. Only F2 is acting. And now the acceleration is something like A2. When I'm writing A2, I should only consider that force which exists in that moment. Maybe earlier there was a force F1 was acting on your body, but now it is not existing. If I ask you what is the acceleration at that present moment, you just need to consider the force at that moment. You have nothing to do with what is the history of the forces that has been acted on it.
So that
Okay.
time no net force.
Huh?
That time will we have to find the net force?
No, not necessary. That is what we are saying. Like if there is a mass M, I apply a force F1, you got some acceleration like A1. Okay. So now the question is, if I tell you to find out acceleration at this moment, what you had to say? A1 is equals to F1 by M. Correct?
Yes.
Now I'll say I'll make my F1 goes to 0. Now no more F1 is acting. Okay. And I'll say like some new force F2 started acting on it. What we got? F2 is acting. Now if I tell you to calculate acceleration, so what do you say? Will it be equal to A1 now, the earlier acceleration? No, right? Because the force is different. So what happens? So A2 will be definitely different, because your F2 is different from F1. So what you get? You get your acceleration as F2 by M. Okay. And what I'm trying to say is, here I'm not adding F1, because F1 is now not acting on the body at the moment when I am discussing. Correct? Yes or no? Can you hear me? Yeah? Am I audible? Can you hear me?
Ma'am, you can hear me?
Yes, yes. I can hear you now. Yeah. So, what I am trying to convey is, at the moment when I'm talking, only F2 is acting. So, its acceleration should be decided only by F2. You no need to think about what was the past force that is acting. Okay. And now I'll give you a different situation. Like the same particle M is there, and at the given moment, both the forces are acting. Like F1 and F2, both are acting. Now what you have to do, your acceleration will be decided by both the forces.
F1 plus F2.
Yeah. And it is not just F1 plus F2, you should take their vector sum. Okay. Understood?
Yes, ma'am.
Understood the meaning of, like, it does not depend on history of the motion.
Yes, ma'am.
Whatever may be the other forces were acting in the past time, we no need to worry about it. If it is existing in the present moment, we have to consider. If it is not existing in the present moment, you ignore it. That's all. Okay?
Yes, ma'am.
Yeah. So there are, like, this question is somewhat like, it's some, some different type of a problem. So we'll work out in a minute. Just we'll have a look about this also. There is a bullet of mass 0.04 kg moving with a speed of 90 meter per second. Like, you are given with velocity and the mass, correct? Enters a heavy wooden block and is stopped after a distance of 60 centimeter. Okay, so let us say there is one heavy wooden block. A bullet fires and it can enter. It can come till 60 centimeter in the wooden block. And it comes to rest means what? Its velocity is becoming 0 now. Do you agree?
Yes, ma'am.
Yeah. So you need to find out what is the average resistive force offered by the block on the bullet. How much is the resistive force? Because it is making the bullet to come to rest. No? So it means it is trying to oppose the motion of the bullet, correct?
Yes.
So we can say like some resistive force. Yes or no?
Yes, ma'am.
Yeah. So in that way, like some force I want to calculate, what I should do, if I want force means I should know what is the mass and acceleration. Do you agree?
Yes, ma'am.
So mass is given, but acceleration is not directly given. We need to find out what is acceleration. So how can we do it? So again, like, you are not supposed to forget our equations of motion, which you have learned in chapter 2 and 3.
Yes.
Okay. Or like 3 and 4 maybe. So it's like, we know that, like, there are 3 equations of motion. V is equals to u plus at, v square is equals to u square plus 2as, and what we have, the other one, s is equals to
ut plus half at square.
Yeah, very good. S is equals to ut plus half at square. The point is, out of these 3, which equation I can use? Because somehow I need to calculate acceleration, right? Yeah. So in all the equation, acceleration term is there. So out of these 3, which I should use?
Initial speed is given.
Yeah.
And second one?
Yes, because anyway there is no information regarding time. Yeah. Correct? So obviously you can eliminate the first and the third one. Okay. And like in the some distance is been given to you, like the total distance traveled is 60 centimeter, correct?
Yes.
That is what given. With a velocity of how much? Initially it has a velocity of how much? Can you tell me?
90 meters per second.
Yeah. It is entering the wooden block with 90 meter per second square. It travels a 60 centimeter and its speed becoming 0. Like its v is 0, its u is 90 meter per second square, correct?
Yes, ma'am.
And s is 60 centimeter. That is how you should take. Okay. And from there I can calculate acceleration. If there was something like at what time the bullet is coming to rest, what you should do? You have to use this equation. Yeah. So that is how you should relate. Okay. So all those, the equations of motion in which you learnt in chapter 3, It is like till the end of the 12th standard, here and there we'll be using. It's not like a formula which is only used in that chapter. Okay.
Okay.
Yeah. And now what we will get? V square is 0 square is equals to 90 square plus
2 into.
Yeah.
So we have to turn
2
60 into meters.
Yes, obviously. Like everything should be in 1 unit, like SI or CGS.
Then
And most
0.6.
preferred is SI. Yes. A into 0.6. Okay. So you can calculate for A as minus 90 into 90. I will write 90 square divided by 2 into 0.6. Okay. 2 into 0.6. So if you can just simplify, and you're going to get an answer like 6750. Correct?
Okay.
So that's what given over there, 6750. Okay. And there is a minus sign here. What is the importance of that minus sign?
The direction.
Direction or something else?
I'm not sure.
Okay. As the bullet is, traveling from this end to this end, its speed is increasing or decreasing?
It's decreasing.
Yes. So that means what you can tell is it is an acceleration or deacceleration?
Deacceleration.
Correct, no? So it's a deacceleration. So that is whenever you have a retarding force, the word is also retarding force is given, correct?
Yes.
It is not mentioned like force. Okay. If you have some force which is trying to decrease the speed, then that means you will have retardation or deacceleration. Okay. In that case, you get a negative sign. Okay. And you had to get a negative sign. If the speed is decreasing, you had to get a negative sign. It's the opposition to the increase in speed. No? So obviously you will get a negative sign. Okay.
Okay.
And now in order to get,
yes.
It's a retardation. Okay. Or deacceleration. Okay. And like if you want force now, what you should do? Multiply by mass into acceleration. You can put a minus sign which will just tell you it's a retardation. Okay. Or a retarding force. Nothing to worry about that. Okay. The magnitude, like if they are asking you magnitude, you can ignore that negative sign over there. Okay. Understood?
Yes.
Yeah. So the next question, tell me.
The force will be 6 minus 6.
Oh, you are working out.
0 into 0.04, yes. Right?
Correct.
Okay.
Exactly. Yeah, the mass is given to you in kg itself, no? So that is 0.04 kg into 6750. Okay.
So minus 269.2.
Yeah. Here they have just rounded it off to 270. Okay.
Okay.
Yeah. So now, moving to next question, that is 5.3. Hope you can see that.
Yes, sir.
Yeah. The motion of a particle of mass m is described by y is equals to ut plus half gt square. Okay. Find the force acting on the particle. This is one interesting type of a problem. So we'll work out this. Like any problem can be asked in this way. Okay. So what you are given? You are given like y is equals to ut plus half gt square. Correct?
Yes.
Plus only given, no? Ut plus half gt square.
Yeah. Gt square.
Yeah. So now you are supposed to find out the force. Correct?
Yeah.
You are supposed to find out the force. Yes or no?
Yes.
So now how do you find out force? Force is like mass into acceleration. Correct? Force is like mass into acceleration. So now, like the mass is just given like m itself, and we have no idea about acceleration. What we can do, but that its position with respect to time is given, correct?
Yes.
So what you can do, like if I want acceleration, okay, one step we will go back. I can say dv by dt. Acceleration is dv by dt, correct?
Yes.
Yeah. And also what is like velocity is also not given. So we'll go one step back. I can say dr by dt or dy by dt, correct? Can I able to say like that? Yeah.
Yes, ma'am.
So in that way, if you like, you are seeing my writing screen, no? It's visible, right?
Yes, ma'am.
Yeah. So now what we will do, one time differentiation will give you velocity, two time differentiation will give you acceleration. So first, shall we find out velocity like dy by dt? Or you can...
You have to differentiate that formula.
Yes, you have to differentiate the given position function. Okay. So will you differentiate with respect to time and tell me?
Okay, just...
Yeah. Try it out. If you don't get, you let me know, okay?
U plus
Yes.
half G2T.
Sorry? U plus half
G2T.
G into 2T. Correct. Correct, no? So now I want acceleration because they are not asking you velocity. So dv by dt. Can you differentiate one more time?
dv by dt. So
yeah.
Ma'am, the half and the 2t can
Yeah, you can cancel. This is just g into t now.
So u plus gt.
Yes.
So u plus gt.
It will be g. Correct. The acceleration is just equal to g. Correct? So, and what else? They have, find the force acting on it means what you will do? F is equals to
m.
Yes, m into a you should do. So that is m into g.
Yes.
It's nothing but the weight of the particle itself we are talking. Okay. M into g is nothing but the weight of the particle. No? So we are just talking about it's the force, which is nothing but the weight. Okay. And you can, I think you can recall it. Y is equals to ut plus half gt square. It's a parabolic equation. Do you connect it to your projectile motion?
Yes.
Correct. No, there we had a negative sign. Like a. Do you remember that?
Yes,
it's a parabolic. Okay. And like they just have concluded, does the given equation describes the motion of a particle under acceleration due to gravity itself, and y is the position coordinate in the direction of g. Okay.
Yes.
Yeah. So any doubt is there in this problem?
No.
Okay. So now we'll move on to define one more quantity, that is impulse. Okay. So what is impulse? Have you come across this term anywhere earlier?
Is it change in momentum?
Yes. Impulse, you can say like change in momentum. Okay, I'll just write like delta P. And this is also equal to F into delta T kind of a thing. That is force into delta T. Like a large force acting in a small interval of time can going to give you a large change in the momentum. Okay. Yeah. Like a short interval of time you choose, like maybe some fractions of seconds. There's some quite large amount of forces there. So if that has been acted on some particle, there will be a large change in momentum of the body. That is what you call it as impulse. Okay. Impulse can be defined as the product of force into the action of time, or which is mathematically equal to your delta P, because we know that our F is nothing but delta P by delta T, correct? Or let me write like dP by dt. Just a minute. So F is equals to dP by dt. If I want change in momentum, it is nothing but F into delta T or dt. Okay. F into delta T. Now, if you want to find out the momentum, so what you can do is like you can integrate the force from given two time intervals, right, over the delta T. So that is actually going to give you the momentum. Like from the problem point of view, yeah, this formula is important. Okay.
Okay.
Yeah.
Deep flow.
You're taking it down? Yeah. So yeah, that's what they have given. You can see equation 5.7 in NCERT. So what they are saying, impulse is the product of force and time duration, which will also comes out to be equal to change in momentum. Okay. So here they have given an example like when a ball hits a wall and bounces back. The force on the ball by the wall acts for a very short time. Correct? It is just you throw a ball, it just hits and come back. It's not like the process of hitting is not a too long time. But definitely the ball has changed its path. Right? So earlier it has one velocity. Now its velocity is definitely opposite to it. Correct? So that means in the small interval of time, a large force has been exerted by the wall, and there will be a change in momentum. That is what you observe. Okay. So in all this situation, the time durations are very difficult. In such case, instead of talking about time intervals, we talk in terms of change in momentum of the body. Okay. Because change in momentum is a measurable quantity. Okay. Because I can say at what velocity the ball has been hit, and I can find out the velocity just after the collision, or after some time if I get I can use v is equal to u plus 8 and I can get what was the earlier velocity and stuff, right? So once I get the initial and final velocity, I can get the momentum also, like change in momentum, because momentum is mass into velocity. Correct. So the action time, finding out the action time is difficult. But it is easy to find out the change in momentum of the body. Okay. So that's why whenever we want to see what was the duration of time force, then indirectly we do by finding out the change in momentum. Okay. Yeah. So there's one more definition given. A large force acting for a short time to produce a finite change in momentum is called impulsive force. Okay. Yeah. Like you can define any way you want. Okay. Yeah. So there is one example again. Hope you can see that example 5.4.
On the back hits.
Yeah. That's also one example. Like when a cricketer hits a ball, the duration where the ball is in contact with the bat is very small. Correct. But definitely, he puts so much effort and it can go for a 4 or a 6 or some far distance it can go. Right. Definitely you see a large change in momentum. Correct.
Yes.
Yeah. So a batsman hits a ball straight in the direction of the bowler without changing its initial speed. Initial speed was 12. Okay. Like after hitting also it attains like 12, but the direction is exactly opposite to it. The mass of the ball is 0.15 kg. Determine the impulse imparted to the ball. Impulse means nothing but change in momentum. You should calculate. Initial momentum is how much? M into V. Correct. Like 0.15 into 12. You have to assume one as positive, the other as negative. Okay. Yeah.
So
Change in moment. Yes. Delta P. Okay, let me write here. So it's like delta P is equals to like P final minus P initial. Okay. So final is like M into it's V, but initially exactly opposite. So one of the velocity should be taken negative. Again, I mean M into minus V I can see. Okay. M into minus V. So it will give you what? 2 MV. Okay. So now you have all the data. You can substitute. Like 2 into mass is 0.15 into V is 12.
In the V should be taken as plus and minus.
Yes,
Plus
yes,
12 minus 1 minus
yes,
12.
yes. Plus 12 and minus 12.
Or
like you can take the way. No. See here. Hope you can see my writing screen, correct?
Yes, ma'am. Yes, ma'am.
Yeah. So MV into like if you are substituting here, like here you have to put 12, here also you have to put 12. That's all. Like already I have taken consideration for the direction and I'm putting minus there. Or else this minus was not there. No. It's like minus 12.
Yes, ma'am. Yes, ma'am.
Yeah. Or if you are using this, you can just say with the magnitudes like 2 into because already I have taken consideration of that opposite direction minus that is giving me 2 mv. So here just 2 into mass is 0.15 into velocity is 12. Correct?
Yes, ma'am. Yes, ma'am.
It's like 36 or 3.6.
3.60.
Yeah, 3.6 newtons. Okay. Yeah, this is how you will calculate the change in momentum. Okay.
Yes.
So now coming to the another important law which may be very familiar, that is third law of motion. So what is Newton's third law? Can you say? Yeah, for every action there is an equal and opposite reaction. So like for every action, like if you like you can imagine like you push some book which is in front of you. Okay. Definitely the book will give back a reaction force. But we can able to overcome that, so we don't see any change in our the direction of the force application. Right? So like you take any example, you apply any force, there will be a reactional force. Okay. So for every action there is an equal and opposite reaction. Like this becomes very important in the case of internal forces. Okay. So for example, if I say there is earth here. Okay. There is earth and there is sun here. Okay. So now if I say there is gravity between them, correct? Yeah. Do you agree? Between the earth and it may be moon, it may be sun, or any other planetary objects. Yeah. There will be a force of attraction between them. For example, if I say the sun attracts the earth with a force of sun is attracting here. I write like SE. Okay. If it attracts the earth with a force of FE, then the earth will also attract the sun with the same force like FES, but in the opposite direction. Okay. In the opposite direction. They're always equal and opposite. If I say sun is attracting earth, it's like it tries to bring the earth near to the sun. I mean, like there are other factors which is deciding. The earth is not at rest. So we are not seeing like the earth coming towards the sun, right? But it is revolving around the sun. That is because earth is not at rest. If the earth was at rest, definitely it would have been captured by the sun. Okay. So the force on earth due to sun. The force on earth due to sun is like attractive. Okay. It tries to attract. In the same way, the force on sun due to earth is attractive. It is like attractive. Both are attractive. Okay. Yeah. So in all the internal forces it is easy to visualize. Okay. So it will always come in pair. The force always comes in pair. That is how we say another way. Okay. Force always comes in pair. Okay. So yeah. I mean that's just there's no much detailation about third law. Like there is one important concept we have to discuss. That is conservation of momentum. Is very important, which we'll discuss in the next class. Okay. Conservation of momentum. Okay. So very important. When The conservation means constant. Okay. So in which situation the momentum of the object becomes constant. That is what we are going to deal. And we'll see what are the importance of that conservation of momentum. Okay. Yeah. So shall we end the session for the day?
Yes.
Yeah. See. Right.